So we're going to continue on with chapter 6. We're going to discuss electric current. The symbol for electric current is capital I. So just to make sure that's clear, capital I. So electric current is going to be the flow or the movement of charge. So remember those electrons we talked about moving around? Well, when we have several of them moving together, it flows. A lot like water flowing in a river bed, electrons can flow similarly. Now, some materials are going to allow for charge to flow easily, and we're going to call those conductors. They conduct electricity well. Some materials will not allow charge to flow, and we're going to call those insulators. But then there's kind of a middle group, some that will allow charge to flow, but only under special conditions, and those are called semiconductors. The formula for electric current is going to be capital I is equal to the amount of charge in coulombs, remember a lot or a little, divided by the amount of time. So it's very similar to power. Okay, the more charge that we conduct over a shorter period of time is going to be a higher current. So the units with this are amperes, called amps, coulombs, and seconds. Now, what are some good examples of conductors? Well, usually they're metals. So silver, gold, copper, steel are all really great metals that are conductors, as is seawater. Seawater is a really great conductor of electricity because of the undissolved ions, or the dissolved ions in the water, sodium and chloride. Some insulators are things like rubber, glass, oil, diamonds, dry wood, styrofoam is a really great insulator. Semiconductors tend to be things that are used in electronic devices, so we don't typically see those a lot in our everyday life like we would conductors and insulators, specifically because those special conditions that have to be met are not typically the ones we see from day to day in your average scenario. Electric resistance is given the symbol capital R. There are four main factors that could contribute to how a material resists charge flow. So whether or not it acts as a conductor or an insulator, there are four factors we can use to predict. The first is its material, which is what we just talked about. If something is a conductor, it's going to have very little resistance. If it is an insulator, it's going to have a high resistance because it doesn't want to let charge flow. So resistance is just as it sounds. It's resisting the flow of charge. That's what it's resisting. The next one is the length. So we have a nice little cute schematic here on the right-hand side to show us what this might look like. So how resistance contributes to length? Well, if we have a very short conductor, the electrons only have to travel very short distances, so there's not a lot of resistance. So soon, made it, yay. The longer that the conducting material gets, the electrons have to travel even farther, and therefore they kind of get tired. Are we there yet? Oh, must go on. And so there's higher resistance as the length of the cord increases. So as the length increases, resistance increases. The third one here is diameter, also called thickness. Sometimes it's called cross-sectional area. It really just depends on the author's text preference, the author of the text preference. But cross-sectional area is essentially this shaded area right here. It's if you cut the cord and looked at it side on to see how thick or how wide that cord or the conducting material was. So if we're looking at that, if we have a very thin wire, you can see here the electrons are having to squeeze through. So it's going to be harder for them to pass through the cord. Versus if the thickness is increased, the electrons are just breezing right through that cord, no problem. So what we see is that as the thickness increases, the resistance decreases because they have more space. The last one here is temperature. And you can see here it's pretty clear that as the temperature increases, so this is a flame on the conducting material, it becomes too hot for the electrons, and they are saying, yow, they are in pain. And so what we see is that as the temperature increases, the resistance increases. The electrons do not flow as easily. You need to know the 4 factors that contribute and make sure you understand the relationship mathematically, so increase, decrease, between the variables and resistance. AC/DC, it sounds like it's a band, and it's not. Well, it is a band, but that's not what we're talking about. AC/DC is going to describe the direction of the charge flow, because that's important. When a current only flows in one direction, that's going to be called a direct current. These are your electrical devices. You put a battery in them, you plug them into the wall, they charge up, and then their battery is charged, but they are operating on a direct current. The current is only going to flow in one direction the whole time. Okay, one direction the whole time. When a current alternates direction, meaning it goes one way, stops, flips, goes the other direction, it's called an alternating current. These, most commonly to us, are our household electric circuits. So we can see here the current is going to go in the bold line, it's going one way. Then at a certain time, it's going to stop, do a 180, and go the opposite direction, and that's what the dashed lines represent. Okay. There are advantages to each of the uses, but most commonly your small portable electric devices are direct currents. Your household circuits, meaning like your breaker box, are alternating currents. So an electric circuit has requirements. An electric circuit must contain an energy source, like a battery or a generator. It must contain conducting wires to move the charges, so that's what this is. And there must be an object to be powered, where the work is being done. Now, there is another common feature of circuits, it's not required, and that's what's shown here. And sometimes this is called a switch. So just like your on-off device or your light switch in your room, whatever the object's on-off switch is, that's what's turning the object on and off. So it can open or close the gap between these wires. So if the gap is open and the wires are not completely in a full circuit, then there's not going to be a light on. But once you close the circuit and you allow the charge to flow, the light bulb's going to turn on. So those are the 3 requirements that have to be there: the battery, the wires, and something to do the work. The switch is often as part of it, but it's not required. So voltage, we just talked about batteries. So voltage is the amount of work being done and the size of the charge being moved. Now, the units of voltage are volts, capital V, that's the symbol. We are familiar with voltage probably most closely with batteries. So the formula is voltage equals work divided by charge. So remember when I said that the little q, capital Q, this is an example where Q is going to be small, lowercase. So most of us are familiar with batteries. We know they have different voltage numbers on them. You may have never looked. I know I probably had never looked until I started looking at teaching this type of stuff in class. So you have a 3-volt battery, 1.2 volt battery. Our AA's and AAA's are 1.5 volts. And then you have anywhere from like 9-volt batteries that you see in fire smoke detectors. You have a 12-volt battery, which is used in your car. And then there's more specific type stuff, which we don't need to worry about. In fact, you don't need to memorize these things. What I want you to realize is that these batteries have voltage ratings. So it tells you how much work can be done by that battery. It tells you the size of charge it could be moved. And typically, the more batteries that are required, the more energy that's required to operate the device. So if you have your remotes have typically 2 batteries in them versus remote control cars may have 4 or 6. So things that require a lot of work are going to require a higher voltage, a higher combination of battery voltage. So if your TV remote has 2 1.5 volt batteries, it essentially is using 3 volts. In a remote control car, if you have 4 batteries, it's using 6 volts. So it's moving more work, a heavier size of charge than your remote control. So then we have to relate the terms we've talked about, which is resistance, current, and voltage. So voltage was the one we just talked about. Then we had resistance, which was our 4 factors, and then we had current, which is the amount of charge moving over a period of time. We're going to call that Ohm's law, which brings us to the units of resistance, which are ohms. So we didn't talk about that when we discussed the 4 factors of resistance, but the unit for that is omega. It's a Greek symbol. And this triangle, which we saw with density, is very similar to what we see here, which will help you remember the arrangement. So if we remember that these always represent dividing, and this represents multiplying, we can see that voltage equals current times resistance is 1. If we have resistance equals voltage divided by current, or you could have current is equal to voltage divided by resistance. Okay, so this is Ohm's law, and this figure will help you remember the different arrangements of the formula, very similar to density. But what it tells us is how the resistance changes as we increase the amount of current running through something, and it can help you determine the overall voltage output. So if we have something that can carry a lot of current, so move a lot of charge over a period of time, but its resistance is very high, it's going to produce a large voltage. If the resistance is very low, we're going to have a very small number. So electric power and work. If you include a time factor with the work done in moving charges, it's going to be called power output, which is very similar to our discussions about work. Remember, we did power equals work divided by time. And this is going to be the power output specifically of the voltage source. Now, electric power is going to be measured in units of watts, which is very similar to what we talked about before. So what's the difference between watts and volts? Well, watts is going to be the method of measuring the rate of energy transfer. Power is measured in wattage. Watts are the products of voltage and current. For example, the higher the wattage, the brighter the light. So we know that a 60-watt bulb, so I'm not right on that, a 60-watt bulb is greater than a 40-watt bulb, brighter. Voltage, on the other hand, is a force that makes the electricity move. The potential difference between the 2 points in a circuit is measured by the voltage, and is measured in volts. If you switch off a light, the voltage is still in the energized part of the circuit. So when you turn the light switch off, or you turn your phone off, there still is power behind the light switch. It's just not on. So now we're going to finish up this chapter with magnetism. The ability of certain materials that have a natural ability to attract iron has been around since at least 600 BC. It's a naturally occurring rock, easily attainable. The Chinese began to use it to make compasses around 1000 AD, so just like your traditional north-pointing compass. Now, the rock to us is now known as magnetite, which has the word magnet in it. And this is a picture of magnetite right here. Now, every magnet has 2 magnetic poles or 2 magnetic ends. We know them as the North and the South Pole. Magnetism is very similar to electricity. It's why we cover it in this chapter after just covering electricity, because like poles are going to repel and unlike poles are going to attract, just like electricity. So we see here, South and North Pole attract, South and South, North and North repel. The same law, Coulomb's law, applies about the force of attraction or repulsion. The magnet can produce a magnetic field just like we talked about the electric field, except for instead of having a charge over here and a separate charge over there, the magnet is going to be one one item. So this is a single magnet, a bar magnet, and it has a north pole and a south pole. Even if I broke this magnet into smaller pieces, so say I broke it in half, it would now have a new south pole here and a new north pole there. Okay, so the magnetic field is built around the single magnet. Another thing that it makes magnetism similar to magnets or electricity is that the magnetism is an inherent property of the material, meaning I can't take the magnetism out of the magnet, just like you can't take the positive and negative charge out of the electron and proton. Now, magnetism is also going to be important to us when we talk about earth science, because Earth has a magnetic field that is shaped and oriented as if it were just a huge bar magnet inside of Earth. You can see here, this is the globe. It has the bar magnet in the middle. Now, something that's probably unexpected to you is that the south and the north poles of the magnet are not pointing towards the north and the south poles of Earth. In fact, the North Pole is pointing towards the South Pole on the United States, and the South Pole of the magnet is pointing towards the North Pole. And on top of that, you have this, the North Magnetic Pole, which is not the same location as the geographic North Pole. And then same thing down here, you have the geographic South Pole, and then you have the magnetic South Pole. And this is called the magnetic declination, which means it's not quite centered like it would be. It's not that the magnetic and the geographic poles are in the same exact place. They're slightly off from each other, tilted by a certain amount of degrees. And you can see here the magnetic declination is about 11.5 degrees. And Earth has a declination. We don't spin on our top like a spin top would. We are actually tilted a little bit, and we're spinning kind of at an angle at 23.5 degrees, which is also going to be a declination we'll talk about with earth science. This should complete our conversations for chapter 6. Please let me know if you have any questions or concerns regarding any of the things